Hey guys, Ms. Gosling here. In this video, you're going to learn about simple harmonic motion, and specifically this is our first HL extension because by the end of this video, you are not only going to be able to talk about what simple harmonic motion is, you are in fact going to be able to graph the motion for an object in simple harmonic motion. So let's go ahead and get started with a little bit of a throwback, hashtag TBT, to circular motion. So we can actually use angular frequency to help us understand circular motion. I wrote circular motion here, guys. I meant simple harmonic motion. Simple harmonic motion. So what I want you to think about is two masses that are lined up. The first one is on a turntable. Now, let's see if I can get a nice circle going here, guys. So here's our turntable. And on this turntable, I have mass 1. This turntable is rotating with a constant angular frequency, omega. And a reminder, guys, angular frequency is essentially how we talk about our angular velocity. Now, with that first mass on the circular turntable, I have a second mass that is on a pendulum. And I have this mass set up so that it is at the same position as my as my rotating circle at all times. So think about when my pendulum is down here at its equilibrium position, my mass on my turntable is going to be here at its far point. Similarly, I can draw my mass in the third position up here. I'm going to number these as 1, 2, and 3, and 1, 2, and 3. But on my mass and my turntable, my pendulum and my turntable mass are going to still be lined up. Then, when my mass on my turntable returns to position 2, and is here now at, let's call it position 4, which again, same as our equilibrium position, my turntable mass is going to be here. So the reason I went through this whole rigmarole here is to help you guys see that we can use angular frequency to understand circular motion. Because defining our position, our velocity, and our acceleration in simple harmonic motion requires us to use that angular frequency. So here what we're doing is we're going to be connecting the angular frequency that we talked about in circular motion to some of the variables and some of the constants in our simple harmonic motion equations for the pendulum and the mass on the spring. So before I do that, I want to talk about displacement, velocity, and acceleration in simple harmonic motion. So we define our position with respect to time in simple harmonic motion as, so this is going to be our position at a given time. And that position with respect to time is equal to x naught, which is our maximum position, times the sine of our angular frequency times our time. Now, folks, I'm going to be doing some calculus here. If you are taking HL math, you should be able to follow along with this. SL math as well, I believe. Now, if you've not had any calculus, you don't need to worry about how I'm getting where I'm getting, but I want you to learn the equations that I'm going to derive for velocity and acceleration. So let's go ahead and jump into some calc. So we know that velocity is equal to our displacement of position, or is equal to our change in position over our change in time, or dx dt. So we want to take the derivative with respect to time of, so we know that dx dt is equal to v, and so we have to take d by dt of the right side of our equation. So of x naught times the sine of omega t. So what I can say is that I know that my x naught is not going to be affected by that. However, I have that omega t inside of my sine that I do have to worry about. So this is a nice chain rule. So I'm going to first take the derivative of sine of omega t, which is going to give me a cosine of omega t. And then I have to take the derivative of that omega t as well because of my chain rule, and that's going to just give me an extra omega. So that tells me that my velocity is equal to x, my initial position, times my angular frequency, times the cosine of my angular frequency times time. So guys, even if you don't know calculus, I do expect you to know this equation here. My third equation is my third derivation is going to be finding my acceleration. So I know that just like how velocity is dx by dt, my acceleration is the derivative of my velocity with respect to my time. So I can say that acceleration is equal to the derivative with respect to time of my velocity equation. So x naught times omega times the cosine of omega t. So again, I don't have to do anything to x naught times omega. However, I have to do a chain rule again with that cosine omega t. So the derivative of a cosine is negative sine, and we're going to leave that omega t the same. And then we'll do that chain rule with our omega t, and that will give us an extra omega. So simplifying that, we have this, that our acceleration is equal to negative omega squared times x naught times the sine of omega t. But hopefully you guys recognize that this here is just my position. It's just x. So I can actually simplify my acceleration equation to my acceleration being equal to negative omega squared x. And I hope, guys, that this is what you're expecting, since we know that our restoring force is directly proportional to our position. We know, again, our restoring force is directly proportional to our displacement, and therefore, and we also know that our acceleration is directly proportional to our restoring force, and that comes from F equals ma. So it should make sense that our acceleration is going to be directly proportional to x, with that extra factor of omega squared in there. So folks who have not had calculus, I do expect you to know to learn these three equations. Folks who have had calculus, you don't actually really need to memorize the equations if you know how to do the derivations, but quite frankly, I recommend you take a look at these equations as well, because I'm guessing you're not going to want to, you may not remember to do the derivation on the IB exam, and you also just might want to have these written down so you don't have to bother with doing it. Okay, so that was a lot of math that I just threw at you guys. Let's talk a little more about how those equations actually relate to the motion of a pendulum. So, and I'm going to use the pendulum. You can replace the pendulum in your head with a spring if you prefer the spring. So the first thing that's important to know is that for simple harmonic motion, we are going to define, let me undo that and make this a little bit less of an ugly circle. We are going to define our equilibrium position as x equals 0. So as you recall, the equation that I started out with was that my position with respect to time was given by x, my initial position, times the sine of omega t. Now, if I look at this equation where t is equal to 0, my position at no matter what x naught or omega are is going to be 0. And the reason for that is that the sine of any number is 0, right? We remember that sine, when we draw sine out, looks kind of like this. So what this means is that when I am using the equation x naught times the sine of omega t to define the motion of my pendulum, my starting point is my equilibrium position. So I am starting my timer when my pendulum is at that equilibrium position, when it's hanging straight down. But what do I do if I want to start at my maximum point instead? Well, let's look at, instead of sine, let's look at cosine. So let's see what happens if I write x is equal to x naught times the cosine of omega t. Now, what I want for this equation is I want to show that and the reason I chose this equation is because at t equals 0, cosine is 1. So therefore, what I'm saying is that my x at time 0 is equal to my maximum position, my highest point, which is, of course, exactly what I want if I'm starting my timer at my highest point. And the reason that I know this is, again, I know that the cosine of 0 is 1. And I can remember that from my nice graph of cosine of time. Well, really, it's cosine omega t, but we're not going to worry too much about that. So again, when we are starting our timer at our minimum position, at our equilibrium point, we will use sine. When we're starting it at our maximum point, we're going to want to use cosine. Now, what this means is when we're starting our timer at our maximum point, we also are going to have to find v and a with respect to time a little bit differently. So taking our first derivative of our cosine equation here gives us x naught times the negative sine of omega t times omega, or negative x naught omega times the sine of omega t. And I can do the same to find my acceleration, which is going to give me negative x naught omega times the cosine of omega t times another omega, or negative omega squared times x naught cosine omega t, or negative omega squared x. So the takeaway here that I would like to leave you guys with is that my acceleration equation is not going to change, but my velocity and position equations are going to flip which trig function they have, and my velocity equation is also going to get that extra negative sign. So let's quickly talk takeaways. So first of all, we can use the angular frequency of a system in simple harmonic motion to determine its position, velocity, and displacement, and that angular frequency is related to that restoring force. We didn't get too much into that because I wanted to really focus on that graphing and on understanding what those equations really mean. That is something that I do want you guys to just be aware of. So anywho, I'm going to go ahead and let you guys go. Best of luck. You have one more HL extension, and then it is your chance to solve some problems.